So that is the kind of the science and the history behind the Nobel Prize in Physics for this year. And what was really exciting was that just literally a couple weeks or less than 2 weeks later, there was another announcement that built right off of this Nobel Prize winning work, which was the first neutron star merger event. And this was announced on October 16th. And what's kind of crazy is that there had been buzz throughout the astronomical community for months that something was happening, but people weren't talking. And I actually heard about it from a colleague at Caltech, and he wasn't talking either. So I knew that there was going to be a big announcement on the 16th, but didn't know what it was. But it's basically two merging neutron stars instead of black holes. And the critical difference here is that neutron stars are made up of matter that's distributed and that can be flung out in an explosion. And the interactions of that matter during the explosion can cause substantial amounts of light that's emitted, create something known as a gamma ray burst. And let's run through that animation again. And just like the black holes, the orbiting neutron stars lose energy via gravitational waves, and as they slowly spiral into together, they lose more and more energy until they merge. And that explosion destroys much of the material and disperses it in the explosion. And there's also a substantial amount of light that gets emitted as gamma rays, and that light can let's run through this again. That light can ionize, and that glow can show up in interstellar gas that's further away from the two neutron stars. And it can take many millions of years for these two stars to spiral together. Actually, the one estimate I heard was about 11 billion years. But once the final event happens, it happens very, very quickly. So here are the detections from the two LIGO detectors. So you can see the signal. And then since the initial detections of the merging black holes, a third detector had gone online. This is the Virgo detector run by Europeans. It's located in Italy. But what's really interesting is that Virgo didn't see anything. So I'll explain why that's important. Now, what was also really exciting about this is that right after the gravitational wave detection, or about 1.7, 1.8 seconds, there was a gamma ray flash that was detected by the Fermi Gamma Ray Space Telescope. And so when that occurred, suddenly there was a realization that there might be an electromagnetic signal from these two merging neutron stars. And so that's when astronomers really got to work. So let's look at these merging neutron stars again. Neutron stars are basically the sort of the cinders of the aftermath of the explosions after the explosive death of massive stars. And they're basically extremely dense objects, about 10 kilometers across, so roughly the size of cities. And again, as they spiral together, they're emitting gravitational waves, and as they're getting closer and closer together, they release more and more of these waves until they merge, and you get this big pulse of gravitational waves. And then here is what the LIGO detector was seeing. So it saw this increase in the signal, and then just less than 2 seconds later, there is this gamma ray burst. And this is a hint to astronomers that there was an actual detectable signal in light, in electromagnetic radiation. And now the problem was where to actually find the source, because it turns out that Fermi isn't doesn't give you an accurate position on the sky. So here is kind of the region of sky that Fermi said the signal was coming from. There was another gamma ray satellite that they could use to sort of localize it even more. And then when they added in LIGO, they were able to narrow it down to that patch. So here is the Virgo Observatory in Italy. And again, normally what they're hoping is that Virgo would have a detection, but one reason why it wouldn't have a detection is if the signal came in from these 4 directions, which are blind spots. And so if, given the fact that Virgo didn't have a detection and that the signal was coming through these blind spots, they were able to narrow the location of this gamma ray burst even more. And there were about 50 large galaxies. And so people started observing through all these galaxies to find the one that had the signal, and they were able to do it. This was, I think, the 8th or 9th galaxy that was observed. And so the Swope Observatory was the first one to detect it, just under 11 hours. But other observatories came online, and they were able to find the aftermath of those merging neutron stars. And in the end, over 70 observatories from around the world were involved. And so there are observatories in space as well as ones on the ground. And I mean, this is massive, or science on a massive scale. There are estimates that anywhere from a quarter to a third of all astronomers working today were somehow involved in this discovery. And so when the announcements came out on October 16th, there were also about 50 papers that were released simultaneously. These are peer-reviewed papers that had been written and were all published on that day. And here is you can see the source dimming over time. This is over about 10 days after its discovery from a telescope in Chile. And there's a huge amount of science that's being done, but probably the one that you heard most about in the news was the fact that these neutron star mergers help create much of the heavy elements that we are familiar with. And so this periodic table is broken down into the types of events that lead to the creation of those elements in the universe. So it turns out that the Big Bang is responsible for all the hydrogen in the universe and most of the helium, but low mass stars and also exploding stars contribute to smaller fractions of the helium. But when you look down here in the very heavy elements, you can see that all the element squares with lots of yellow in them, those came out of merging neutron stars. So in the aftermath of that explosion, you have a huge number of neutrons and atomic nuclei that are merging and colliding, and they lead through something, through a process known as our process nucleosynthesis to create heavy elements. So this is gold, right? And so most of the gold that we have on Earth came from merging neutron stars. And similarly, iodine is a trace element that we need for our thyroid gland to work properly, and pretty much all of it is originated in merging neutron stars. So the really exciting thing, I mean, there's going to be more and more science coming from not only this event, but future events that will occur. But one exciting takeaway, at least for now, is the fact that we ourselves here on Earth have this immediate connection to the greater cosmos through the fact that all these elements that are part of our everyday lives, gold, silver, lead, iodine, came from these exploding neutron stars. Now, not necessarily the one that was just observed, which is 130 million light years away, but there were merging neutron stars in our own galaxy that probably seeded these heavy elements in the interstellar medium, which eventually found their way into molecular clouds, which formed the next generation of stars, including our own sun and solar system. So with that, I'm going to hand it over to Steve. Thank you.